All right, thank you so much for joining us today. We are hosting our first webinar of the year, and this is our 45th episode of Graph Gurus. And today we're presenting smarter AI with analytical graph databases. And before we get started, we'll go ahead and just introduce Victor, or actually I'll go through the housekeeping items first because we have a question here about if the webinar is being recorded, and we're going to go ahead and email it to you. So if you have to drop off, we'll be emailing it within the next couple hours after it's over with the slides and the links that that you can follow up with. And right now, if you do have questions on the content during the presentation, you can ask questions at any time via the Q&A tab in Zoom. And there's a picture of it on the slide here. And you can also chat with us directly, and it will be available. Someone has asked me if the meeting will be recorded and if it will be available offline. Yes, it will, and you'll get the email as I said. So with that, I'm going to go ahead and pass it off to our host today, Victor Lee.
Thank you, Emily. It's great to be here with you today. I think I may have done Graph Gurus #1 a couple of years ago, and I've done various ones through the series, and so here we are at number 45. So this is exciting to be here, a new year. And one thing that is new for today is normally our webinars are 1 hour long. We're trying to keep this 1 to 30 minutes, so I'm gonna try to get right to it. I may take up 30 minutes with the presentation, and the Q&A may be following that. So let's get going. So graph analysis, Gartner has said, is possibly the single most effective competitive differentiator. So if you want to make yourself stand out to be better than the competition, taking advantage of graph analysis is perhaps the most important thing you need to do in terms of managing and using your data. So what we're going to talk about today is, if you're new to the topic, what is a graph database? And in particular, what is an analytical graph database? And then talk about why graph plus AI, the main topic for today, and then to talk about 3 basic approaches for implementing graph plus AI with some use case examples. Those 3 being unsupervised learning, feature enrichment from graph features, and in-database learning. So types of graph databases. There are 2 major flavors: semantic or knowledge graphs and property graphs. And they have a lot of things in common. They both have entities and connections between entities. That's the basic thing that a graph is, sort of nodes and connections between those nodes. The differences come into where a semantic graph thinks in terms of individual facts, and then you have an ontology which you sort of use alongside or on top of those individual facts to provide an interpretation model of understanding those facts. And it's good for pattern matching, and based on some of the conventions built into the RDF standard and the OWL standard, that there are standard ways of interpreting those relationships, and then you can do logical inference and inductive reasoning because of those standardized interpretations of what those connections mean. A property graph is more general purpose. It doesn't have those predefined meanings. You construct whatever structure you want. You have a node, you define what's in that node. You have a connection, you define what's in that connection. It can be all sorts of properties, different values. Because of this more streamlined, do exactly what you want design, it tends to be higher performance. And it also is better for the more computational type work, where knowledge graphs are good for logical reasoning, and property graphs excel at large scale analytics. And again, for both of those, you can also think in terms of transactional, where they guarantee that data updates are, if you may have heard of the ACID properties for relational databases, they guarantee that each transaction is clean, so to speak. It's guaranteed that it occurred correctly if it happens at all, and that different transactions don't interfere with each other. Analytics is really emphasizing the computational workload, the ability to define and execute more complex analytics. And where TigerGraph sits in this space is we are a property graph. We are transactional and analytical, or hybrid transactional analytical. So a property graph excelling at analytics, also executing transactions. So why would you want to use a graph or a graph database or graph analytics with AI? Well, it's because of the data model of being able to represent relationships as sort of a so-called first-class element. It really enables you to describe data in a much more natural way. It's really thinking about knowledge graphs. This is the way we represent knowledge. This order shipped to location number 2. How more clearly, plainly can you express your information than that? And because of the way this is a native graph database represents these relationships as links, if really getting down to at the code level, a pointer, it's much more efficient than relational databases, which try to join different tables, and where the join is not a native structure. It's a added work it has to do after the data is stored to try to figure out how things are related. So it gets you, and because you can represent as many different types of relationships as you want, you really have much more richer, more densely representative, a more dense, compact way of representing information. From that information, you can ask deeper, smarter questions, which are more semantically natural. And therefore, because of that efficiency, you can search farther and wider. So within a given amount of time, within a given amount of compute resources, you can accomplish more complex computations. You have the ability to execute graph algorithms, and then the graph enhanced machine learning that we're going to talk about today. And lastly, because you're able to represent your data in a directly meaningful semantic way, when you get a computational result or a machine learning result, the result will be explainable. You will see very clearly, oh, it's making this prediction because of this pattern of orders being purchased, etc. So some possible, here are some real world examples from some of our customers, which other companies I'm sure have similar situations. Healthcare, large healthcare companies such as Optum are using it for real-time recommendations. They've constructed a 1.3 terabyte so-called graph brain, and they're using it for real-time care recommendations, which both improves healthcare and lowers the cost for everyone. Industrial supply chain. A supply chain is obviously a graph, but when you take into account all the factors that large industries have, they have not just where are things coming, but what are the business terms? What are the delivery terms? What are the different options for their products? Again, and then trying to make predictive analytics of what forecasts and trying to maximize the return. What should I produce in order to get the most revenue, also to lower the risk, to take advantage of, what do you do when there are disruptions? So one of our companies or customers, Jaguar Land Rover, they were able to reduce the analytics that used to take them 3 weeks down to 30 or 40 minutes, weeks to minutes. Basically, this was almost unusable. Now this is something that you can just quickly try different scenarios. So that's saving them, again, millions per year. And thirdly, financial institutions, whether it's banks, whether it's retailers, which have a lot of financial information, insurance companies, or at this, we've now entered tax season, whether it could be, in companies that help with like Intuit that have tax preparation software and accounting software. By integrating information from their large customer base, again, you can do, or looking at the financial data looking at financial data, we can do much better fraud prediction, anti-money laundering detection. So now I'm going to talk about the 3 different ways that graph can be used for AI and machine learning. And the first way is just directly running queries or graph algorithms, which just turn out to be very dedicated queries. So mathematicians have come up with numerous graph algorithms over the decades, and you can fit them into a handful of different categories. The most basic is just tracing paths through the graph, trying to find the shortest path, for example. Another is trying to find natural groupings. So you have these connections. What do the connections have dense areas versus sparse areas? Do you see areas, oh, that looks like a cluster because of there's more dense connections over there? And trying to do that from a analytical way rather than doing it a visual way. When you have millions and billions of entities, you can't do that visually. You have to do it computationally. And ranking and centrality, trying to find out which are the most important, which are the most influential, which are the most centrally located entities. Again, if you're trying to do any kind of analysis of dispersion, of how do things spread, whether that's for positive benefit, for trying to analyze the best way to market something, or negative, where are the centers of disease spread and how can I nip it in the bud? We have algorithms for that. PageRank turns out to be a ranking and centrality algorithm. Similarity, based on where are 2 entities that seem to have similar neighborhoods. If you look around that node and look at what types of neighbors and how many neighbors it has, well, that node, even though it's not connected to that node, there's no direct connection between that one and that one. If you look at their surroundings, they have similar surroundings. So that's a graph locational similarity analysis, and then frequent pattern discovery. When you look beyond the individual connections, again, as we've been talking about, look for where does that environment look similar to that one, which you might think of that as a pattern. Its neighborhood represents a pattern. You can define all sorts of patterns that you're looking for, which are like little mini subgraphs. And where do I see that frequently? All of these are what you might call unsupervised learning, because we're not telling it to look for anything in particular. We're telling it, that is, I haven't given it an input and said, find this. What we're saying is, I have some characteristics. Tell me where those characteristics kind of show up. Tell me what's similar. Tell me what's frequent. Tell me what's central. And that is one form of machine learning. One way that's used in healthcare is to find the most influential healthcare provider within a certain region for a particular medical specialty. So let's say this is a graph of patients and providers and service claims. And how can we find who is most influential? Well, if you use the PageRank algorithm, we could find that in this case, this Dr. Thomas, he has high PageRank because there are a lot of other doctors who are making referrals to him, and many of those doctors themselves may be relatively influential. So if a lot of influential people are referring to you, that makes you even more influential. Second question, okay, now that we know he's influential, who is he influencing? Who is the community of people that he influences? So then we could run a community detection algorithm and define that, okay, here's sort of the spread, here's the region, here's the scope of influence that Dr. Thomas has. Another algorithm, another graph analytics that can be used for unsupervised learning is to find similar entities, in this case, similar patients. This display is mapping out this patient's, Doris Smith's, medical care journey, different types of engagements she's had with the healthcare system over time. And there are a couple red flags where she hasn't received proper care, and we want to find, are there other patients who have a similar pattern like this so that we can take intervention and provide the preventative care to make sure things don't get worse. So in this case, they have this dashboard. All you do is just click on this button. Well, what's happening when you click on that button? What it's doing is it's saying, say, Doris is like patient A. And patient A has these different relationships, W, X, and Y. And these are the weights of how important or how strong that relationship is to these factors. This could be how many times has she seen a cardiologist? Did she experience a certain medical incident, et cetera? Each of those represents a different factor. And there's also a different strength indicator. B is another patient, and we see that B also experienced X and Y and Z. So it has X and Y in common with A, and you look at the weights, the strengths. So if A and B have a lot of overlapping factors and with similar weights, we say they are similar. So, if it were not just X and Y, but X, like say it were 10 factors that they had in common, we might say A and B are quite similar. It would give you some score. And that is what is happening behind the scenes when you click that similarity button. Here's another larger application or sort of bigger picture case where similarity is important. Say these represent different entities, persons in a database. Let's say you've merged data. You are a company like Xandr does the analytics for AT&T Time Warner. So they have data coming from multiple sources because that company has many divisions. They get customer information from many different sources. These are 7 different people across their merged data set. However, in some cases, they may actually refer to the same human person. It's not necessarily 7 different physical persons. It's just 7 different entries in the database. By running this similarity analysis, we can find different similarity scores between these different entities. And what we see is, okay, there are high scores among A, B, C, and D in the 90s. And then also over here, E, F, and G. But between C and E, it's only a 65. It's fairly similar, but not that strong. So we can, after we have these similarity scores, we can then do a grouping, a community, if you will, and say, okay, we determined based on these very high scores that these 4 digital entities are actually the same human entity, Barry Markin. And these 3 digital entities are in fact the same physical entity, Beryl Markham. So that's way that graph and similarity algorithms can be used for entity resolution. I'm going to move on to case number 2, where, so we talked about unsupervised learning with graph algorithms. Now we're going to talk about more traditional machine learning, but during the data preparation phase, the data is in a graph and you detect graph-oriented features to enrich your feature set, because the better and the more features you have available for your training data, the better machine learning result you're going to get. So in this example, we have China Mobile, the national telephone company in China. So with hundreds of millions of customers and billions of phone calls per week, this is a phone graph or a call graph. So each node is a telephone, and each link is a phone call. And what they did was they worked with us to identify 118 different interesting patterns of calls. Like a stable group is a set of neighbors to this hub node that they call on a regular basis. So if you call this person on a regular basis, you're in the stable group. If once more, the people that you call each other, then that's a sort of a in-group. You form a little community. So it's detecting, is there an in-group of people who call each other who are your neighbors? And then this is a chain where, say, number 1 called 2, who called 11, who called 3, who called, and 3 actually, you called 3 also. So there's a loop here, and they said, is there a relatively short loop of length, size 2 or 3 connections like this? So they had 118 of these different features, and those get stored in a feature vector, like we do in traditional machine learning. So we have the graph data. We run queries to collect this data. So now this phone has these 118 values. This phone also has, every phone has these feature values for itself. You put that into the machine learning system, you get your result. The goal is to predict unwanted calls. What is the behavior of unwanted, maybe scam phone calls? And by doing this, they were able to construct a real-time good phone call, bad phone call detection system, which in a fraction of a second, for the incoming call, for a new phone call, it quickly extracts the 118 features, scores it against the machine learning model, and tells you before you even answer the call, do I want to answer this call or not? You probably have, we have systems like this for the US telephone providers now, but this was done 5 years ago using our graph system. And that's just following up on the same thing. And now we're getting into how does this sort of fit in, what's the whole pipeline? So we have the graph data, in this case, the phone and phone call graph. We do the feature extraction to produce enriched training data. The data is exported to whatever is your favorite machine learning platform. It then produces a model. What the model says is if you provide me with a new feature vector, I will apply these weights to the different features, and based on summing those weighted values, I will give you a score, and that score will tell you is this fraudulent or not in this case. And so you use the graph for the original data gathering, the feature extraction, and you use it for applying the model. So the graph is not just for preparation, but the graph becomes operational. You use it in the live system. And why is it explainable? It's because, again, remember, each of these features, they make sense. There is a semantic meaning to what is a stable group. There's a semantic meaning to what is an in-group. So these are meaningful, human understandable features. And so the model is likewise human understandable. And that brings us to our last way of actually taking that machine learning and doing it in the graph. Well, previously I was taking the data, exporting the data. Now there's a new class of algorithms which are like neural networks. A neural network, of course, is a graph, but you don't need a graph to execute it. But there's a new family of algorithms which are really designed natively for being trained in a graph. So what you do here is you take your data, again, bring it into the graph. You do the feature extraction to enrich it. Then you do your in-graph training. So now a platform like TigerGraph is capable of doing that because of the way TigerGraph is designed as a native parallel graph database. It has the scalability and speed that you would need to do machine learning. Machine learning is computationally intensive. If you do it on the wrong platform, it's just going to be too slow. But with TigerGraph, because of its performance characteristics of being able to execute things in parallel, and with the GSQL language, being able to execute algorithms. Machine learning is set a sequential, complex, iterative algorithms. Not every graph database is really oriented towards doing that type of analytical work, but TigerGraph is. So you can do in-graph machine learning, you get your model, and the advantage here is I never had to export the data. I didn't have the added step of having a separate platform and doing export and import. And I'm always dealing with the most current data because I'm using my source of truth data. And so you have a much simpler pipeline and much faster. And quickly, an example, we can do this with, we have several examples on TigerGraph Cloud and in other webinars. We had one that did movie recommendation. You can find this in Graph Gurus episode number 28, or you can go in TigerGraph Cloud and select the low rank approximation machine learning version 3 starter kit. We have about 5 different starter kits, excuse me, which relate to machine learning. And this is just one of them. So I'm not gonna spend too much time to go over the details of this one. It's using the latent factor approach. And it basically, given a set of movies and a set of people who reviewed movies, where they reviewed some, but they didn't review every movie, it tries to predict how would you rate a movie. If you were to see that movie, what would you think of it? So it's predicting that that Alice would give a 4.5 rating for this movie called Cute Puppies of Love. And to say a little bit about some of those in-graph machine learning algorithms, there are embedding approaches which try to take the graph structure and reduce it to a linear structure. And there are graph neural networks. There are several flavors. I'll take a quick look at graph convolutional networks and then wrap up for today. So a traditional neural network, you have your input layer, you have your output layer, and you have one or more hidden layers. So these are variables. In this case, these would be the nodes of the graph. So each node of the graph, it represents some entity. And this represents sort of what the prediction you want to make. What is the output what are the factors? There might be just like one thing because you're just trying to get a yes or no answer. Or here there are 4 things. What you do, and then there's this mesh of connections between each layer. And these represent synthetic imaginary variables. These are not real world variables, this hidden layer. But so you have these imaginary factors that say, okay, this input determines that set of variables, which then determines this one, et cetera. And you can translate this into matrix algebra, where you form a matrix for the input layer, which we call X. Excuse me. The pattern of connections we'll call P for propagation. And this is hidden layer H1, H2, H3. So H1 is equal to, I'm sorry, I skipped, I should go back here. H1 is equal to X, which is the input, multiplied by the pattern of propagation, P, so P times X. And take that, apply another function called the activation function. It's sort of the threshold. How strong does a signal have to be before it flips the state? And so it's a simple matrix multiplication from one stage to another. When you do a graph convolutional network, you add in another matrix called the adjacency matrix. And I should have a picture here. Too bad I don't have a picture. But the adjacency matrix is basically saying, what is the pattern of connections? This propagation layer has nothing to do with the graph. It's connecting everything from here to there. It's not the graph. It's just every possible connection from here to there. The adjacency matrix is saying, what are the actual connections from this vertex to that one, or from that one to that one? So it's actually representing the graph. So adjacency matrix is the graph. And then you're just basically putting that into each step, you're taking that topology into account. And that's the basic idea behind a graph convolutional network. So lastly, I gotta wrap up. I've reached my 30-minute limit. So why is analytical graph databases, why are they, and why is TigerGraph in particular suitable for this sort of machine learning AI workload? It's the performance characteristics which you get from the real-time deep link querying and the ability to handle massive scale, because we're talking big data, right? Graph databases, when they first came out, they got a reputation for being slow. But, modern graph databases like TigerGraph, which are we're implemented in C++ for highest performance. We have distributed data architecture. We have a parallel processing architecture, and we compress the data so that there's less data to work with, so everything goes faster. We're the only graph database that has all of those factors for performance. And then lastly, we're the only graph database that uses an analytical query language like GSQL, which is Turing complete, which can handle SQL-like queries. If you look at our latest release, 3.1, we actually directly support some SQL commands. But we also allow you to encode graph algorithms. And so those algorithm-based, analytical-based workloads just fit so naturally within TigerGraph. So wrapping up, graphs are a great way to represent knowledge and information and the way that people think. You have richer data, and then they fit naturally with machine learning 3 ways. Through unsupervised learning with graph algorithms for things like the similarity algorithms, the entity resolution, the recommendations that we went over. You can do neural networks for deep learning, and you can extract graph features, which provide richer data no matter what machine learning technique you're going to use. For supervised learning, better features are better. And again, because the natural way that it represents information, the semantic clarity, you get explainable AI. So, and platforms like TigerGraph are great for this massively parallel processing that you need. So I'm going to turn to my questions. I'm start to answer some of these questions that I got. So let's see. First one, are there any use cases for BERT and OpenAI? I'm not sure what GPT is. BERT, I know is related to natural language processing, NLP. Yes, there are a lot of people who are starting to use TigerGraph for NLP. We'll be working up an example. We have customers who are trying this out. We don't have a demo yet, but we can follow up more with you on that. Oh, I see, and you do have a link. Great. Is there a book you can recommend that has clear descriptions of not just what all the graph algorithms do, but also how they work? So if you want to understand how, so when I was in grad school and I studied graph algorithms, let's see, the book is on my shelf here. This is a general purpose algorithm book by Corman. It's one of the standard textbooks on algorithms by Corman and 3 other authors. But there's actually a lot of online websites you could go to today. What I would recommend is if you go to docs.tigergraph.com to look up our graph algorithm library. We give a description of each one at a high level. And what you could do is if you follow up with me, I can give you a pointer to maybe where I'm trying to understand what level of depth you want to go, and I'd be happy to help you there. Okay, how can you handle data privacy? We've got some great new features for that. The multi-graph feature lets you set up, obviously, the basic model used in all databases to sort of isolate who can see what. First, you have role-based access control. And in relational databases, you have row-based security and also column-based security. And the analogies to that in a graph are vertex-level security and property-based security, where only certain users, only certain roles can see these vertices. So in 3.1, we introduced vertex-level access control exactly for we've been thinking about it a long time, but we were driven by some customers in healthcare. So take a look at that feature. We'll be doing a webinar on that in the future. Can you share the sizes of data involved? Well, we have, like I said, the China mobile use case with the anti-fraud or unwanted phone call detection. They had hundreds of millions of phones and
Yeah, I
billions
think
of
he was referring to the healthcare graph that you mentioned.
the healthcare. Well, okay, so is that the similarity? So the similarity, I believe there were tens of millions. And let's see, is there any solution to, and again, also the performance on that would be, I believe, on the order of a second to search the database and find any similar patients. Um, is there any solution to include a time frame information on graph? I think you're just sort of asking about. So definitely you can treat time as a property, right? That's time, date, time are native data types, and you can filter. You can use the standard filters for selecting things within a time range. There are additional sort of special features in so-called time series databases. A lot of those things you can just do natively, and also with our index feature where you can index properties. So if you put an index on your time, date, time property, you can get a lot of the capabilities. But we're also on our roadmap. We're planning some additional features, more custom features to provide even more custom capability for time series analysis. Can you direct us to a GSQL tutorial? Well, if you go to docs.tigergraph.com, you should find a tutorial section right there. And does any tool ingest PBI dashboards? I'm sorry, I don't know what PBI stands for. So I could look it up, but let me just move on to the next question. What sets your software apart from other open source graph software? We talked about the performance capabilities. We are the only native distributed graph database that does both as real-time updates. So we're the only graph database that has the combination of being native, that is designed as a graph database from the ground up. So the storage is graph at its heart. Distributed, that means we scale out to multiple servers as many as you need. And real-time updates that, unlike some that are read only or fast for read, slow for write, we are fast for read and write. And that's really what distinguishes us, plus the analytical capability and the Turing completeness of the GSQL language. Are there plans in TigerGraph to support the null types? Yes, there are. That will probably, there's something called the GQL standard that's coming along for query languages. I'm on a committee with other graph database vendors to have a standard query language called GQL, and GQL has null. And so when we introduce, there will be a period when we will be supporting both GSQL and GQL, and since GQL will require null, we'll have GSQL will also support null. And so that's looking in sometime next year. For Python guys, who's the ML library to learn? I was just having a meeting this morning where we have a project called PyTigerGraph, which you can find on GitHub now. And we're talking about the roadmap for PyTigerGraph. And it supports a variety of, it makes it possible to work with really the Python library of your choice. But what we're talking about is how to make it even more convenient and natural. So I would just take a look at PyTigerGraph, and you can go on our community to ask more about if you have a particular question. Somebody just put down Power BI.
That was the description, or the question about PBI. PBI stands for Power BI.
Okay.
Yeah. Does anyone
To ingest dashboards. We're not going to ingest the dashboards. We're going to connect to, just like normally you would set up Power BI to talk to your database. Your database is the source and Power BI is the dashboard. We're going to have that capability very soon, this first half of this year. Does Tygraph support graph database with tight schema depending on the use case, like semantic interrupt? So when you say tight schema, so one thing is Tygraph is schema based, as opposed to there are some other graph databases which are schema free or schema less, whereas you don't, in those, you don't define any schema in advance. You just ingest data. The data could be any types and you have what you have. And so it doesn't impose any rules. So it is not managing your data. Tygraph, like relational databases, you define your data types first. So I have for example, a person vertex, and a person has these properties. I have a doctor vertex, and a doctor has these properties. I have a patient visits doctor edge type, and it has these properties. So you define your schema first. And so I'm wondering if that addresses your need. We're also sort of in that schema, you basically can have that essentially is establishing your constraints for what is considered valid data or not. And again, when we talked about the security earlier, you would also, at the same time, you could represent who is allowed to see what. And I think we're at the last question. What is the maximum size the graph database is auto-scaled to do now? We say auto-scale. So within first of all, there is no fixed limit. There's no program, there's no software limit for maximum size. You can, in theory, you can have as many vertices and as many edges as you want. You're just limited by the storage capability of the system that you have deployed. And again, it's going to depend on how complex is your schema. So if you have a complex vertex, you're not going to be able to have as many of them. If you have very streamlined, very simple schema with not very many properties, then you'll be able to have more vertices and edges. So it's really dependent on how much memory you have available and how much disk you have available for the graph size. Wow, so that was a really, I hope I got to all the questions I saw. Again, if I missed some, you can contact me, victor@tygraph.com. And I'm gonna, I think, just hand it over to, I think Emily is still here.
Mm-hmm.
I'll let her wrap up.
Okay, great. Yeah,
Thank you,
everyone, if you want to go ahead and try Tygraph, you can get started with Tygraph Cloud, which has many of the algorithms that Victor mentioned today. We have starter kits, really easy to start. It's free. There's no credit card required. We also have a enterprise edition, and it is a free license up to 50 gigabytes of storage that you can use for production and non-production use. We also have Test Drive, which is an online demo that it's pre-built with all the data, so you can test it out that way. We'll send you all these links in the next couple hours. We also offer certification, and we have a great community site where you can ask many of these questions, and we will get back to you right away. But I think on the next slide, we're talking about the next workshop that we have. Victor, can you move to the next slide for me?
Mm-hmm.
Okay, there's Tygraph Cloud. We'll send you the links to that, or you can just go to tygraph.com/cloud and start for free, like I said. And next week, we're hosting a workshop, and it is a hands-on workshop where you will do the step-by-step walkthrough of Tygraph Cloud, and you'll use one of the starter kits for fraud detection. And it's 90 minutes again, so it's a little bit more intensive. And so we hope you'll join us for that. We'll send you the link to it. And I think that is it. We really appreciate your time today. If we missed any of your questions, we'll go through those and make sure that we go ahead and send you an email directly.
Yeah,
So
thank you so much. I appreciate it, and have a good
yes,
start to this year.
thanks everyone. Bye.